Welcome to Chemical Equilibrium. So the truth about reactions. While we generally don't talk about it throughout most of the year, some chemical reactions are reversible. A reaction that is reversible can go both forward from reactants to products and reverse from products to reactants. If a reaction is written as A plus B goes to C, that indicates that it's only going in the forward direction. To indicate that it's reversible, you would change the arrow to a double-headed arrow so that you could see it's going both forwards and backwards. A and B would still be called the reactants because they are on the left side of the arrow, and C would be called the product even in a reversible reaction. This way we can just keep straight which things we're talking about. So even though technically the products are still acting as reactants when the reaction is going reverse, we always refer to the things that are on the end of the arrow as being the products. Reversible reactions can reach a special condition which is called equilibrium. Equilibrium is often described as a dynamic equilibrium because the system is constantly changing. The reactants do not stop once an equilibrium has been reached, so the reactants are changing to products and products are changing to reactants. Essentially, the whole thing is just constantly doing something, so it's never a static system. Equilibrium is specifically defined as a situation where the rates of the forward and the reverse reactions are equal and the concentrations of the reactants and products are constant. These two things have to be true at the same time. If the rates are equal, that means as soon as you make some product from reactant, some of the product is going back to form reactant. So the overall amounts in reactants and products should remain constant when the rates are equal. So these two things are interdependent on each other. So a graphical representation of concentration and rates for a system that reaches equilibrium. The first one we're going to look at is for concentration. So here, at the start of the reaction, there are only reactants, so the concentration of our products would start at 0. So in this case, the red line indicates the products. And here they're indicating that could be either CO2 or H2O. The brackets around those again mean concentration. The reactants are carbon monoxide or water, and that's indicated by the green line. At the beginning of the reaction, we should only have reactants, and we should have no products, assuming that's how you're starting. As the reaction progresses, the concentration of the reactants should decrease and the concentration of the product should increase. Once the system reaches an equilibrium, the concentrations will remain constant, but they don't have to be equal to each other. You'll notice here that there's a lot more product once equilibrium has been reached than there are reactants. The other way to look at this is with a reaction rate. So here, at the start of the reaction, there are only reactants, so the rate of the reverse reaction would again be 0, which makes sense. There's nothing there. You're not going to be able to go backwards. As the reaction progresses, the rate of the forward reaction will decrease from its initial high because it's got so many reactants at the beginning. The rate should be pretty high, lots more collisions going on. And the reverse reaction is going to speed up, which makes sense because as you're making more and more product, the reverse reaction rate is going to increase because, again, there'll be more particles of the products to collide together, allowing for more reaction rate to occur. In order for the equilibrium to be reached, the rates must become equal. So here, they actually do have to reach the same level in order for equilibrium to be reached. So pay attention to what's being shown to you when you're looking at these representations, because if it's concentrations, those don't have to be equal to each other. They do have to be constant, though. But rates, they do have to be equal. So here we have another particle diagram that's illustrating a reaction that's starting with 100% reactant at the beginning and is going to form some products. It's a reversible reaction. So at time A, the image shows 100% reactants. As the reaction progresses, it will contain a mix of reactants and products. When the amounts of reactants and products remain constant, the system has reached equilibrium. At what time does that first happen? So if we look at the particle diagrams here, you'll see in time A, it's all reactants. If you look at time B, we have 1, 2, 3, 4, 5, 6 of our reactants remaining, and now we have 2 new particles of products. Time C, we have 1, 2, 3 particles of products and 1, 2, 3, 4 particles of reactants. And if you look at time D, we have 1, 2, 3, 4 particle of reactants and 1, 2, 3 particles of product. So the next question is, what time does the system first reach equilibrium? Well, equilibrium is defined again as when the reactants and products amounts remain constant. So that first occurs at time C, because from C to D there's no change in the net amount of reactants and products. While the particles themselves have changed from reactants to products, the overall quantities of both have not. So again, dynamic equilibrium. They're not going to stay as what they are. They can change back and forth, going forwards and backwards, but the overall amounts needs to remain constant. All right, factors that affect a system at equilibrium. So once a system reaches an equilibrium, it can be stressed and then have to find a new equilibrium. This means either that the forward or reverse reaction will speed up to try and achieve a new equilibrium. Which reaction speeds up depends on what stress is applied. So what are the stresses that cause this to happen in a chemical system? They include concentration, pressure, specifically for gases, and temperature. The other thing we need to talk quickly about is a catalyst. We'll do that at the end. These stresses are referred to as Le Chatelier's principle, which I'm sure you remember from honors and regents. So we have three examples, one for each of the stresses. The first one we're going to look at is concentration. So our reaction is shown here. It's nitrogen plus 3 moles of hydrogen go to 2 moles of ammonia. These are all gases. So here the system is at an equilibrium with a mix of nitrogen, hydrogen, and ammonia. Okay? So the larger blue circles are going to be your nitrogens, the smaller ones are hydrogens, and then you have NH3 illustrated there as well. Now the stress here is that we're increasing the amount of nitrogen, as you can see in letter B. This is going to disturb the equilibrium that was established and cause the reaction to shift either forward or backward to find a new equilibrium. Because nitrogen is a reactant, the reaction is going to shift forward to achieve a new equilibrium. So it's going to need to use up some of that new nitrogen that was added. In order to do that, it's going to use up some more of the hydrogen that was there, and it's going to increase the amount of nitrogen present. So if you compare the illustration in B to the illustration in C, you'll see that the amount of hydrogen has gone down and the amount of ammonia has gone up, which makes sense because if you're going forward, you're going to be using up hydrogen and increasing the amount of ammonia. The next one we're going to look at is pressure. So pressure will only affect the equilibrium of a system that contains gases as either reactants or products. When pressure is changed, we're really looking at a change in the volume or space available. When pressure is increased, as you know from the gas law unit, the volume is decreased, and when pressure is decreased, the volume available is increased. So here we have our picture, again same system with nitrogen, hydrogen, and ammonia. We have our equilibrium system in A. In B, the container has been shrunk due to an applied pressure, so there's less space available. And then if you look at C, this is the effect of that increase in pressure. So if you look at the particles from B to C, which way did the reaction shift? So take a look at what you have in your containers. So in B, we've got 1, 2, 3, 4 particles of nitrogen, 1, 2, 3, 4, 5, 6, 7, 8 particles of hydrogen, and 2 particles of ammonia. Now if you look over to C, now I only have 2 particles of nitrogen, which is a decrease. I've got 1, 2 particles of hydrogen, and 1, 2, 3, 4, 5, 6 particles of ammonia. So this indicates to me, based on my reaction, that it's gone forward. I have less nitrogen and hydrogen than I had, and I have more ammonia. So why? Why is it doing that? So in the most simplified terms, when you increase the pressure, there is less volume or space available. So the system is going to shift towards the side with less moles of gas, since gases take up the most space. So our reaction was this again. You have a total of 4 moles of gas on the reactant side and 2 moles of gas on the product side. Therefore, when the pressure was increased, your volume was decreased. The reaction is going to shift towards the side that has less moles of gas, or towards the ammonia side, because they will take up less space. So let's take a second and go back. Look at your picture. There's a lot more particles there in B, which are going to try to take up more space, apply more pressure, than if you look at C. C's got a lot less particles because when you go forward, you reduce the total number of particles that are created. Temperature. So increasing the temperature will speed up the rates of all reactions due to an increased number of collisions. This is from chemical kinetics. So no matter what you do when you increase temperature, both reactions are going to speed up. But there's a second factor playing a role here. Now temperature is the only thing that's going to change what's called the equilibrium constant. So when you change the temperature, you're already changing the equilibrium, but there's a secondary effect as well. Okay, so there are, however, still shifts that will occur in a system due to a temperature change because some reactions require energy, or endothermic reactions, and some reactions release energy, which are exothermic. So when temperature is increased, it will cause a shift to favor the endothermic process. In very simple terms, this happens to use up the extra energy that's provided. So when you add temperature, now you've created too much heat, so you need to use some of that heat up. The process that uses energy is the endothermic process, so that reaction will be favored. When temperature is decreased, now the system needs to replace that energy, so the exothermic process is favored. Again, the reverse. If you take away heat, now you need more heat, so you need the reaction that's going to create more heat. That's the exothermic process. To determine which process is endo and which is exo, the delta H of the reaction must somehow be provided. So either you need to calculate it, or it's given to you, or there's some experimental observation you can use to help predict which way is endo, which way is exo. So here's our example. So our reaction is 2 moles of nitrogen dioxide is in an equilibrium with dinitrogen tetraoxide. Nitrogen dioxide is a dark brown gas and N2O4 is colorless. As you can see, when the temperature is increased, so you can see where it says hot water, the reaction vessel becomes much darker. And when you put it into ice water, the reaction vessel becomes much lighter. So trying to figure this out, you can use your observation skills here and the fact that you know NO2 is dark brown and N2O4 is colorless. When you are increasing the temperature, there is much more NO2 present. And when you are decreasing the temperature, there's a lot more N2O4 present. So based on this, which direction is endo, which direction is exo, and where should I put the delta H in the equation? Okay, since an increase in temperature shifts the reaction in the reverse direction, the reverse reaction must be endothermic. Therefore, the forward reaction must be exothermic. So the delta H should go on the side with the N2O4, because when I add heat, the reaction produces more nitrogen dioxide. I know this because it got darker. So the delta H needs to go on the opposite side so that when you increase the heat, it will shift it towards the NO2. Right, the last thing we need to talk about for shifts is catalyst. So a catalyst is something that speeds up a reaction by creating an alternate reaction pathway that has a lower activation energy. The addition of a catalyst will not, however, shift the reaction in either the forward or reverse reaction. It will speed up both reactions equally because it will reduce both reactions' activation energies. So here we have a diagram which shows an uncatalyzed reaction and then a catalyzed reaction. The uncatalyzed is the red one. Catalyzed is the purple, so as you can see the activation energy has been lowered, which allows the reaction to progress at a lower required energy. So here's the thing, the change in the activation energy from uncatalyzed to catalyzed is the same for both the forward and reverse reactions. So it's going to speed up both reactions equally. It's not going to cause a shift one way or the other. All right, the last thing in our review is an equilibrium constant, or KEQ. This is also called the mass action expression. And KEQ is written by taking the concentration of all aqueous and gaseous products over the reactants and raising each to their coefficients as exponents. You do not include solids and liquids because their concentrations do not vary. For example, if we have 3W, which is a solid, plus 2 moles of X aqueous, is in a reversible equilibrium reaction with 3 Ys, which are gases, plus 2 moles of Z, which are aqueous, your KEQ would be written like this. You would take the concentration of Y cubed times the concentration of Z squared over the concentration of X squared. We do not include W because it is a solid, so any solids and liquids are just left off. If you want to put something in place of those, you can add a 1. In our previous courses, we primarily used molarity or concentration as our measure for KEQ. This expression can also be written in terms of pressures for gases because a pressure is proportional to the concentration for a mixture of gases, using the idea of the partial pressure law, PT equals P1 plus P2 plus P3, etc., and PV equals nRT. You can label your K as a KP, meaning in terms of pressure, and it's related through the following equation. Kp is equal to Keq times RT times raised to the change in N. So where R is equal to 0.08206 liters atmospheres mole K, T is equal to temperature in Kelvin, and delta N is equal to the moles of the gaseous products minus the gaseous reactants. If you're dealing with only gases, you can pretty much just use Kp in place of Keq without having to change back and forth because it's pretty much equals each other out anyways. But just so you understand, there is a difference between the two things. KEQ, again, the only thing that changes KEQ's value is temperature. So if you change the concentration of one thing, everything's just going to shift around and find a new equilibrium amount, but your K isn't going to change. This allows you to solve for any unknown concentration if you're given the other amounts to start with. So here you can see there's 3 different experiments here with different initial concentrations, and then at equilibrium they all have different concentrations, but your K is constant at 6.02 times 10 to the negative 2. All right, that's the end of our review. There's of course a ton of math to do with this, which we'll cover in the lecture. Chemical equilibrium is covered in chapter 13 in your book. It's probably going to be a good idea to read through that chapter and take a look at the super fun math that's involved in this unit. The bookwork is posted on the website. You can also take a look at the equilibrium tutorials that are available on the website that might be helpful in clarifying some of this information for you. So feel free to look at that, and I'll see you in class.